So let's go for your final topic of quantum mechanics. And this is very interesting one. So we have to go for a scattering, and we will learn how to solve the scattering problem. And solving a scattering problem is quite easy than formulating the scattering problem. Okay. So what should be rule? What should be the basic concept, and what should be the basic assumption behind the scattering is very important. So what I have planned for you, today I will start with the classical scattering. So today we will try to formulate classical scattering, because unless until you are not understand the basic concept behind this scattering, it is very difficult to formulate the quantum mechanical scattering. Okay, so first we have to just formulate a classical scattering. And in this, we will try to solve one or two problem. If time allows, we can go for more than that. And then we will try to formulate quantum mechanical scattering. And in the quantum mechanical scattering, we will see that direct solution or complete solution is next to impossible. So we have to approximate our solution by two methods. The first method is Born approximation, and second method is partial wave approximation. And we will try to learn all this thing in a coherent way such that each and every dot should be connected to each other, और आपको कुछ भी याद नहीं करना पड़े. ये हमारा मेन एजेंडा होगा पूरी की पूरी टॉपिक को कवर करने के लिए. ओके, आई थिंक माय बोर्ड इज क्लियर टू यू एवरीवन.
यस सर.
है ना, बोर्ड क्लियर है? जस्ट अ मिनट. Okay, so let's first we will go for some basic definition, and this definition is very important. So what is scattering? What we will do actually in the scattering? So we have, suppose there is some potential. You assume this is some potential, and this potential is short range potential. That means the potential will be decay at plus infinity as well as minus infinity, if you can see. So it is just going to short range potential. So its area is, or its range is something very small range potential is there. And what we will do, we will send the particle from very far away with some energy E. And the particle will come, and as it will come to the range of this potential, influence of this potential, it will just deviate from its path, and after then again it will go into a straight line. And in general, we will try to solve all this problem for a spherical symmetric potential. Means my potential is only and only function of R in general. So this is a spherical symmetric potential, and they are mainly short range potential. So let's try to formulate the basic definition and all this property of scattering. So first I have to give you first definition, and this is nothing but the intensity, and this is identified as I, and which is intensity. Now, so what is intensity? Intensity is nothing but number of particle. So this is nothing but number of particle crossing through unit area perpendicular to incoming beam per unit time. So this is all about per unit time. Okay. This is all about intensity. So if I am talking about intensity, that means number of particle which is coming, and this number of particle coming through unit area, some unit area, and that will be, suppose this is my, suppose particle is coming something like this. Suppose this is particle is coming, so then unit area is this space. The perpendicular unit area, it is just going to this thing. So this is nothing but the number of particle passing through unit area per unit time. So per unit time, we are measuring basically number per unit time. So this is all about intensity. Now what we are going to do, look at, first we have to see what we are going to do in the whole process experimentally, because scattering is more experimental, less theoretical, but we have to discuss mainly theoretical thing. What we will do, suppose here is our source of potential. Here is potential, and these are some small range potential. So I have give it the some spherical shape. Suppose this is my potential. Now particle is coming in a one particular direction. Let's say this incoming direction is Z direction. What can be possible? The particle can come and it can go something like this. Particle can come, it can go something like this. Particle can come, it can go something like this. Isn't it? Particle can have all, after the interaction of this potential, the particle can spherically scattered. It is coming just like a one direction, unidirectional thing, and after then it can just go to the spherically scattered thing. So it is just coming and it can go like this. It is just coming and it can go like this. So what we have to do? We will just try to figure it out how many number of particle is coming here. And after then we are putting the detectors at the different angle of theta. And the different angle of theta, we are just putting detector, and we just want to see how many number of particle is coming into this particular detector, and this detector has some cross section area. So how many number of particle is coming to this particular cross section area? This is the whole idea. And the number of this particle, the scattered particle, will dependent on which kind of potential it is going to scatter. So this is main thing we have to cover. So mainly we have to cover, actually we are measuring nothing but number of particle coming and number of particle scattered per unit area. And we can see how this area can change. If we will change the area of this particular detector, then obviously no more number of particle will come here. If I will decrease the area, less number of particle will come here. So let's see how we can make it mathematical thing. So before that, let us go for one particular more definition, that is differential scattering cross section. Differential scattering cross section. So different book have different notation. Goldstein have taken this thing as sigma, but I will not take sigma, because sigma I will take for the total scattering. So for the differential scattering cross section, what we can find, we can take the notation d theta, and obviously we can take phi also, d theta phi, but phi is not relevant because my potential is spherically symmetric. So if it is spherically symmetric, the all value of phi, it has same cross section. So it is just, you can just imagine that something is coming here, that if I will fix the area at the angle theta, I can have different value of number. But if I am rotating in the whole 2 pi angle, then I will get the same thing. I will just discuss when we will go into the figure. But right now we are just try to understand what is this particular differential scattering cross section. And this is the most important thing. And this is nothing, number of particle, and we can write thing as differential scattering cross section into d omega. So let me clear it. We have differential scattering cross section into d omega. D omega is some solid angle. Why we are taking solid angle, we will discuss also. and this value is equal to number of particle scattered into solid angle d omega per unit time by incoming intensity or incident intensity. Now, if so, now this is number of particles scattered from the solid angle d omega per unit time, and this is incident in intensity. And what is incident intensity? That number of particles crossing per unit area perpendicular to incoming beam. So can you please tell me what will be dimension of this one? What will be dimension of this one? D theta d omega. From here, number of particle is there also, number of particle is there also, per unit time is also, per unit time is also, but here we have per unit area also, isn't it? So everything will be cancelled out dimensionally and per unit area will go upward, and so why this differential cross section is nothing but the dimension of area. Are you people going to understand this thing?
Yes, sir.
है ना, ये समझ में आ रहा है ना? This is nothing but some kind of area after the scattering, because it is incident intensity will just tell you number of particle crossing per unit area perpendicular to incoming beam per unit time. And here we have also per unit time, number is also there, so number cancel, per unit time will cancel, and finally you will have area on the denominator, and you can easily compare. This thing is nothing but the dimension of area. So real challenge into scattering is that how we are calculating this particular differential area, and we have to make the theory to calculate this particular differential area. So let us try to go for a basic theory of understanding this particular differential area. By the way, do you understand what is solid angle? What is solid angle? Solid angle is something kind this. Look at what is going to happen. Some particle is coming. There is, let's say, this is your range of potential. And what will happen? You just want to make one differential area, and at some angle theta, okay, at some angle theta, and it will cover the all this particular thing. So this will be some solid angle, and we have to calculate this particular area, okay, and this area is nothing but the differential scattering cross section. Are you getting my point? This is source of potential. The particle is incoming, and after then it can scatter into different direction, because there is not only one particle, n number of particle is coming. So what will happen? It is coming here, it will come to this particular influence, and after then what will happen? It can go into different direction. Okay, it will go into different direction, and we will just try to measure this particular d theta, because this is nothing but area, this particular d theta at angle theta for, and if you are just going to rotate is completely, suppose we are taking this angle theta, we can take this angle theta and we can rotate it completely, then obviously we will just cover the all possible space. Because what I am saying, the particle can come here, it can go like this. Particle can come here, it can go like this. Particle can come here, it can go straight also. If you have very high energy, then it can penetrate and it can go straight also. Depends on which kind of potential we have. But this potential is really slow range potential. What is the meaning of that? Meaning of that, after the scattering, if we are going for the high value of R, very high value of r, for very far from this, the particle will behave just like a free particle. And if it is coming from very far, it will also behave like a free particle. Only at to this region of influence, it will just try to deviate, and after then it will just go for as a free particle. So this is very important thing. So let us try to go for what are our basic construction of differential scattering cross section. How we can calculate this differential scattering cross section. The real challenge is, all main challenge है ना, real challenge is how to calculate this particular differential scattering cross section. So let us try to go for calculation of
सर
हाँ बताओ
सर, वो जो ऊपर एक छोटा सा डिफरेंशियल एरिया है वो डी थीटा है या डी थीटा इंटू डी ओमेगा है?
डी थीटा क्या बोल रहे हो? डी थीटा इंटू डी ओमेगा, बेसिकली डी थीटा इंटू डी ओमेगा बेसिक, बट हम तो एरिया की बात कर रहे हैं ना, सो एरिया तो यही होगा. एट गिवन एंगल थीटा यू विल हैव डी थीटा, है ना. आप जब पूरे को कर लोगे तो क्या आएगा, सारा का सारा, जब ओमेगा में हम इसे इंटीग्रेट कर देंगे तो सारा प्रॉपर एरिया आ जाएगा ना, टोटल एरिया आ जाएगा. ओके, so this is basically d theta into d omega. So this is particularly your d omega. This angle is basically your d omega, है ना, and this area is all about your d theta. अभी देखते हैं, अभी एक एक चीज क्लियर हो जाएगा. Now look at what is going to happen. Suppose this is my line of action, and let's say this is my z axis. So I am sending the particle through z axis, and here is source of your potential. Okay, and you can have, suppose this source have some spherical region. So I can just virtually make one sphere where this particular source will act. Okay, and in this region particle will just behave a free particle. Into this region particle will also just behave like a free particle. So what is going to happen? Suppose from this distance we are sending the particle from distance b, and this b is identified as impact parameter. So what is impact parameter? When we are sending the particle, when it is free, so here my particle is free particle. Okay, free particle, and you will send the particle obviously from some distance from the reference point, reference line, and let's say this reference line is my z axis. Okay, so this is my z axis, and the distance from the distance of a particle from the reference line is identified as impact parameter. So b is identified as impact parameter. Okay, and what is direction of v? That is exactly perpendicular to b. This is your direction of v. So you are just sending the particle exactly perpendicular to this particular b. Now what will happen? The particle will come here almost a straight line, and it will go into this region, and finally it will just deviate into this region, and finally again go to a straight line. So this kind of situation is there. Okay, and this angle, that this particular angle, we are making the asymptotic this particular angle, because this is curve path. Okay, this is something curve path. So if you want to make the angle, you have to make angle with the straight line. So this angle, this is the asymptote of the scattered particle. Okay, this is nothing but the asymptote to the scattered particle. This is okay. This is asymptote to the scattered particle. This is also asymptote to the scattered particle. Okay. Now, this angle is identified as scattering angle. I am just saying this is capital theta. Okay. This angle is identified as scattering angle. Here particle is again free particle. Here particle is again free particle, and this is my origin. So this is my origin. We can assume this is my origin. Now look at here what is going to happen. Here we can make a circular area, and we can make something like this area, ring shape area at the b distance, and this value is, this ring have length dB. So this ring has length dB at the b distance. Okay, so this has length dB, something like this. Okay, this is length b and this length is dB. Okay, this is the thing. Now look at what will happen. The particle is coming through this particular area, and I know its intensity of a particle is I. And obviously this is perpendicular to this particular incoming wave. So this is just a perpendicular to this particular incoming wave, and you are coming here. My figure is not absolutely symmetric, so it will very symmetric figure. Okay, so it will just a symmetric figure. Okay, now can I claim, hence the particle is free here, the particle is free here, and can I claim if I will throw the particle from this side, this will again follow the same track?
Yes, sir.
Why? Because it is classical in nature. We are just talking about the classical picture of a particle. So its path will be exactly same. And only into this region it is going to deviate. Okay, only into this region. Now, this value is basically deviate the whole path into two symmetric thing. Okay, are you people try to understand this thing? About this particular point, we have exactly same type of incident wave, and after then same type of scattered wave. So means I can say my whole picture is symmetric about this point. कह सकते हैं इसे? And what is this point? This point is nothing but R minimum. And this angle is angle identified as psi. So if this is deviated it by the exactly symmetric way, then this angle psi must be also this angle psi. Are you people comfortable? यहां पर ये सबसे ज्यादा इंपॉर्टेंट है कि ये दोनों एंगल सेम क्यों है, एंड व्हाई दिस इज आर मिनिमम. लुक एट, अभी जैसे कि हम लोगों ने पढ़ा था सेंट्रल फोर्स प्रॉब्लम, हम लोगों ने पढ़ रखा है, एंड इन द सेंट्रल फोर्स प्रॉब्लम वी हैव concept of R minimum and R maximum for sun and earth system. You remember all this thing?
Yes, sir.
Okay, so look at, go for this, then you can easily analyze this particular thing. So we have some elliptical orbit, isn't it? And here is my origin. This is my R minimum. You remember? What is my angle theta? What is my angle theta? This angle is theta and this angle is R. So we can make angle theta with the R minimum. We can measure angle theta with the R minimum, isn't it?
Yes, sir.
Yes, sir.
Remember this thing? And what is this? This thing is my R minimum. Okay, this thing is my R minimum. And now what is my polar distance? What is my R? This can be R. This can be R. Okay, this can be R. This can be R. In one side, exactly same R is also there. Exactly same R is also there. Exactly same R is also there. So this angle I can say this angle is nothing but my polar angle theta. Please don't confuse with this scattering angle. This is entirely different thing. Theta, we are just measuring from z cap, but our motion is in plane. And we are using the central force problem because my potential VR is only function of R. So are you people going to understand what is your R and what is your theta?
Yes, sir.
Yes, sir.
Now, again मैं फिर से बता रहा हूं, ये बहुत इंपॉर्टेंट है. You have this kind of situation, okay? You have this kind of situation. Look at here. This is your R minimum. Look at this is your R minimum. And hence it is symmetric about this particular hole. Hence it is just a unbounded system. I can say this is my R. Then what will be this angle? This angle is theta. And again I can talk about different R. Then this angle is what? Also theta. Are you getting my point? So when this, you will get this particular psi. When you will get theta is equal to psi.
Sir, when R
Sir,
is
when
at
R is
maximum.
infinity.
Exactly. So that is all about psi. So when R tends to infinity, you will exactly land at here, na? Because asymptote will meet at the infinity to the any curve. This is all theoretical definition of asymptote. So what is this particular thing? When R tends to infinity, my polar angle theta tends to psi. Now you can understand what is your psi. Yes?
Yes, sir.
Okay.
Yes.
Now this is all about psi. So you can have something like this, and here we have, and we can just divide it into two parts. Why? Because it is symmetric about R minimum. Only one R minimum is possible, and this angle is my scattering angle. So I am writing it with the capital theta, and this angle is some psi, and which is identified as periapsis argument. What it is identified as? Periapsis argument. Now look at what we are going to do in the here. Into this particular part, let me make it clear, and then we will try to see what will be your differential scattering cross section and how we are going to calculate it.
सर एक बार फिर से बताएंगे वो पेरिएप्सिस आर्गुमेंट आर मिनिमम है या साई है?
Psi argument means angle always.
ओके ओके सर.
Periapsis means minimum distance. Minimum distance का जो argument होगा.
यस सर.
Okay, that is all periapsis argument. That is known as psi. Okay, so what we have relationship? We have relationship psi plus capital theta is equal to pi. है ना? So we have this relationship. So you can have 2 psi plus capital theta, and this is a scattering angle, is equal to pi. And this psi is basically polar angle into 2 dimension. Are you going to remember? When R tends to infinity.
यस सर.
है ना? So ये confusion बिल्कुल ही clear हो जाना चाहिए कि हम क्या कर रहे हैं. Okay, so this is very interesting. Now let's try to go for a formulation of all this. So let me make it again. So last concept we have to just understand here. Now look at here. So I can make a smaller picture because this is the thing, and obviously the particle is coming and it is just going like that. This distance is again same. This angle is my capital theta, which is a scattering angle. So there are a lot of thetas, है ना? And this distance is fixed. This is your R minimum. Now, and obviously we have some influence. I can go for one particular sphere also. This is our some sphere also, where we have influence of this particular potential at O. This is my Z axis. Okay. Now this is my z axis, and this is in a plane because motion is central in nature. So what we can do? We have a, let's say, let's make it little bit more. Okay. So what do we have? We have something like, in this sphere we can make one ring. Okay. And this angle, look at this angle is d theta, because you can make d theta up here lower also, and this is your cross section area. This is your cross section area at the angle theta. You can have theta upward also, you can have theta downward also. So this is your cross section angle. So what is this? This thing is nothing but one type of ring with angle d theta, and here this differential is basically d theta. This differential angle here, we can just go for, at some angle theta we can just make one particular area, and let's say this is your area, and this differential is identified as d theta for the given value of theta and phi. So why? You will just have some cross section, some solid angle, so it will look, ये कैसा आपको दिखाई देगा? It will look something like this, isn't it? With respect to origin, ऐसा ही दिखाई देगा ना? Okay, something like this. So this will just look like a solid angle, just look like a solid angle, and this particular angle we have to calculate, and this is shown here. And if you are going to calculate all this thing, then obviously you will just calculate the all particular area of a scattering, jahan jahan se particle aapke scattered ho rahe hain. And you will surprise that from every d theta we have different number of particle. Every d theta we have different number of particle for the given value of theta. So let's go for a conservation of number of particle. So, and initially what we are going to do, we are sending the particle from some area, and this area can be from this ring. Okay, this ring, and this ring has width dB. So what will be incoming particle? So incoming particle is number of particle incident intensity into 2 pi b into dB. This is number of particle per unit time, isn't it?
Yes, sir.
This is nothing but the number of particle per unit time. And what we have? We have d theta d omega is equal to number of particle which is scattered, है ना? Number of particle which is scattered per unit time, है ना? Number of particle which is scattered per unit time in a solid angle d omega by intensity, है ना? By incoming intensity, isn't it?
Yes, sir.
Yes, sir.
है ना? By incoming intensity. Now, so number of particle per unit time in the angle d omega is, can be written at by d theta d omega into I? Yes?
Yes, sir.
So number of particle scattered per unit time is equal to d theta d omega into I, and this is nothing but the I intensity. Yes? And now look at here. This is also number of particle. This is also number of particle. We are just have assumption that we are not losing any particle. The wall particle is coming, have to be scattered. So both number of particles should be same, isn't it? So what will happen? This incoming particle must be equal to a scattered particle. So we have I into 2 pi b dB is equal to d theta. And what is d omega? And I have I also. What is d omega? d omega is 2 pi sine theta d theta. This is nothing but the solid angle d omega. So you know the definition of solid angle. And from here, this 2 pi is cancel out. This I is cancel out. And we have a d theta. And this d theta can be written as b upon sine theta db upon d theta. And yes, we have to take all the thing into mod value because d theta is nothing but the area. And this is definition of differential scattering cross section. So what is real challenge? Real challenge is how you will calculate the differential scattering cross section. But thing is that you have to write, and this is nothing. This small angle is all about scattering angle, okay? D theta, okay? This is a scattering angle. So don't confuse with this angle, okay? This is your d theta. This is your d theta, okay? Don't be confused with that angle. Okay? So this is your main challenge. So what is the main challenge? The main challenge is that how you will write impact parameter B as a function of theta. If you are able to write impact parameter B as a function of theta, you can easily calculate the differential scattering cross section. And once you can easily calculate the differential scattering cross section, you can calculate the total scattering cross section. And what is your total scattering cross section? Is d theta sine theta d theta d phi. D theta into d omega is basically total scattering cross section. Sometime what you can get, sometime you will get your impact parameter is independent of theta, maybe in some cases here. Then what will happen? Then you can use this formula as d theta can be written as b upon sine theta db upon d theta, and here we have sine theta d theta d phi. So sine theta d theta is cancelled. You can go for 2 pi outside and you have b square by 2. So you can write pi b square. So sometime you can use the total scattering cross section also equivalent to pi b square. Are you people able to understand what we are going to do?
Yes, sir.
So real, हाँ बताओ.
सर ये जो स्कैटरिंग एंगल थीटा है वो तो समझ गया, बट वो उसके पीछे जो थीटा है वो एक बार आप बता दीजिए वो कैसे, वो क्या है?
देखो समझने की
जो
कोशिश करो.
फिगर में
पोलर एंगल थीटा की बात कर रहे हो, आर थीटा वाले थीटा की बात कर रहे हो, है ना? स्कैटरिंग एंगल तो समझ गए आप, ये है ना?
हाँ सर, यस
है ना? दिस इज आल्सो फंक्शन ऑफ
जो
थीटा.
डायग्राम उसके पीछे है.
देखो ये जो है, दिस इज आल्सो फंक्शन ऑफ थीटा. डोंट वरी अबाउट दिस. दिस इज आल्सो फंक्शन ऑफ डी थीटा. ये तो हमारा स्कैटरिंग एंगल है. और कौन से थीटा की बात कर रहे हो आप?
सर ये जो फिगर में और एक वो आपने ओरिजिन से बनाया ना, जो
दैट इज द
रिंग के लिए
सेम थिंग.
बनाया
दैट इज सेम थिंग. मेरा फिगर उतना अच्छा नहीं है. जस्ट आई एम टॉकिंग, जस्ट मैं ऐसे बना रहा हूं. लुक एट हियर. ठीक है, ये एंगल, ये मान लो हमारा सेंटर है. ठीक है, एंड दिस वैल्यू, दिस इज योर स्कैटरिंग एंगल थीटा. उस थीटा पर आपने एंगल लिया डी थीटा. एग्रीड? और ये जो आपका एरिया बनेगा, आर यू गेटिंग दिस थिंग? ये जो एरिया बनेगा आपका, ये एक सॉलिड एंगल ही बनेगा ना?
यस
स्फेयर की तरह सोचने की
ये
कोशिश
सेम ही
करो.
एंगल है मतलब.
हाँ, दैट इज डी थीटा. थीटा एंगल पर डी थीटा आपने लिया, तभी तो कोई एरिया बना पाओगे,
यस सर.
है ना? सो दिस इज द सेम डी थीटा एंड दिस पर्टिकुलर इज आइडेंटिफाइड एज डी थीटा. ठीक है, डिफरेंशियल स्कैटरिंग क्रॉस. तो स्कैटर्ड होने के बाद इस एरिया में कितने नंबर ऑफ पार्टिकल आएंगे, वी आर जस्ट गोइंग टू कैलकुलेट.
यस सर.
है ना? सो दिस इज बेसिकली योर डिफरेंशियल स्कैटरिंग। और ये क्या है, ये पूरा का पूरा आपका एक सॉलिड एंगल की तरफ दिखाई देगा। यहां पर मैं बना नहीं पा रहा हूं, बट इट विल जस्ट लुक लाइक समथिंग लाइक दिस। ओके, कुछ इस तरह से वो दिखाई देगा, है ना, कुछ इस तरह से आपको दिखाई देगा ये समथिंग लाइक सॉलिड एंगल। ठीक है, ये एरिया। अब एरिया को इस तरह देखोगे, स्फेयर के पार्ट को, स्फेयर का किसी भी पार्ट को आप अगर कट करोगे तो क्या दिखाई देगा, ऊपर वाला पार्ट, लेकिन अंदर तो पूरा सॉलिड एंगल आता है ना। जस्ट
Yes,
एक
sir.
एप्पल लो, एप्पल का पूरा पार्ट को थोड़ा कट करके निकालो तो कैसा नजर आएगा आपको, उसी तरह तो नजर आएगा। सो दिस इज ऑल अबाउट योर दिस पर्टिकुलर डिफरेंशियल एरिया इज देयर। नाउ लेट अस गो फॉर, और एक और थीटा के बारे में बात किया था, वो थीटा समझ में आ रहा है क्या है? दैट थीटा इज एग्जैक्टली पोलर थीटा, है ना, जो हमने सेंट्रल फोर्स प्रॉब्लम में किया था। आर यू गेटिंग दिस थिंग?
Yes, sir.
है ना, तो वो एक डिफरेंट चीज है। दिस इज योर डिफरेंशियल स्कैटरिंग क्रॉस सेक्शन। एनीवे, सो लेट्स ट्राई टू डू वन प्रॉब्लम, है ना, प्रॉब्लम्स करेंगे तो ज्यादा बेटर समझ में आएगा आपको। Now look at what is the, this is very simple problem, but it will just clear your all concept. So this is your hard sphere, okay, of radius r. Some particle is coming from here and it will just go and scattered. Okay, what we have to do, we have to calculate the total scattering cross section. Total scattering cross section. So obviously this is your reference line, so I can have this as my reference line, and this angle is basically what? Scattering angle, you can say. This angle is a scattering angle, parallel hai to, yes, this is your scattering angle. And this distance is what? Your b. This is your r minimum, that is your r, and this angle will equal to, let's say this angle is alpha and this angle is alpha, same as psi. So particle is coming here, it will collide to this particular thing and it will go like this. So this is your particular situation. What you have to do, you have to first calculate differential scattering cross section, and then you have to calculate basically scattering, total scattering cross section. So what is your real challenge? You have to write b as a function of scattering angle theta. How you will write b as a function of a scattering angle theta? Now we have this value, this is just a parallel. So what is this value? This value is b. And what is this angle? What is this angle? This angle is alpha. Okay, so this angle is alpha and this value is b. Now, and this value is r. So we can write b by r is equal to what? Sin alpha.
Sin alpha.
Okay, and we have alpha plus theta is equal to pi. So what is alpha?
Yeah.
Alpha is nothing but pi by 2 minus theta by 2.
Theta by 2.
है ना? So b by r is equal to sin pi by 2 minus theta by 2. So we can calculate it from this geometry. From this geometry we can easily calculate what is value of b as a function of a scattering cross section. Sorry, a scattering angle theta. So what is my b? B is nothing but r cos theta by 2. Now we have to calculate differential scattering cross section. So what will be my differential scattering cross section? D theta is equal to b upon sine theta and db upon d theta. So what is dv upon d theta? R minus cos theta by 2 into 1 by 2. यही होगा ना?
Yes, sir.
And you have to take the mod value, so there is not any problem. And what is b? B is also given as r, सही लिख रहा हूं ना? Sorry,
तो
cos
sin
sin
theta ना?
theta, that is sin theta. That is sin theta. Why cos? This is sin theta. So here is r cos theta by 2 by sin theta, and we have to write r sin theta by 2, and we have also 1 by 2. So what is this value? So you can multiply with 2, divide by 2, then this is sin theta and this sin theta is cancel out, and you can have value d theta as r square by 4, isn't it? This value of d theta is nothing but r square by 4. Now we can easily calculate the total scattering cross section. So what is your total scattering cross section? The total scattering cross section sigma is nothing but d theta and sin theta d theta d phi. And what will be this value? This value is, you have r square by 4, we have, and what is sin theta d phi? क्या होगा? sin theta d phi is 2 pi,
4.
है ना? So sorry, this
Sir,
will be 4 pi.
Pi.
So 4 pi into r square by 4, that is pi r square. So look at here. So we have the total scattering is equivalent to pi r square. So what is pi r square? Pi r square is just a radius of, so this is your spherical thing. Okay, so this is your spherical thing. So out of this sphere, the scattering will take place from, and what will be the surface area of this sphere? 4 pi r square.
Sir,
So
4 pi r
out
square.
of this 4 pi r square, only pi r square will take part in the scattering. Only from this particular total pi r square, the particle is going to scatter. This is all this meaning. But in the quantum mechanics, you will see the thing will entirely change. That will be, the thing will go, due to superposition of wave, this thing will change. यहाँ तक कुछ पूछना है तो पूछ सकते हो.
सर वो r स्क्वायर बाय 4 कैसे आया? क्योंकि 2 से मल्टीप्लाई डिवाइड किया ना, तो वो
r by 2 है एक पहले से,
sin
एक और 2 आ गया नीचे,
yes, sir.
है ना? एक 2 तो है पहले से, 2 से मल्टीप्लाई किया तो 2 से डिवाइड कर दिया, तो ये वाला sin 2 थीटा का फॉर्मूला यूज कर लिया, है ना?
Yes, sir.
नहीं, देखो ये r हो गया, 2 से डिवाइड, मल्टीप्लाई किया, 2 से डिवाइड भी किया, और ऊपर क्या आ गया? cos थीटा बाई 2 sin थीटा बाई 2, और एक हाफ है ही पहले से, ठीक है? और नीचे में क्या है? sin थीटा. तो ये sin थीटा और 2 sin थीटा बाई 2 एंड cos थीटा बाई 2 कैंसिल आउट. सो व्हाट यू विल गेट? एंड वन मोर r इज देयर ना, एक r यहां भी होगा, एक r इसका वाला b वाला r, और एक r, तो यहां पर r स्क्वायर बाई 4. ठीक है?
Yes, sir.
है ना? एक r b के थ्रू और दूसरा r db अपॉन d थीटा के थ्रू, तो r स्क्वायर तो होना ही है. ओके, एक बार आप ट्राई करना, सिंपल है, कुछ नहीं है इसमें, खुद करोगे तो बेटर समझ में आएगा. ओके, so I think you have understand all this thing. So let's go for a construction of Rutherford scattering. And this is very important, how we can construct Rutherford scattering and how we can understand all this thing. करें क्या उसे? Rutherford scattering?
Yes.
है ना?
Yes.
So let's go for this. Now, so we have this kind of situation. And I think, as I assume, here is my center. This is my, okay, this angle is theta. This angle is your alpha, you can take psi, you can take. Goldstein have taken psi, and some people and this Griffith have taken alpha. So you can take anything. But you know, this is nothing but the argument of periapsis. And what is this value? This is R minimum. Okay. For the Rutherford scattering, VR is nothing but K upon R. This is positive one. So this is repulsive potential, isn't it? So Rutherford scattering is for repulsive potential. And what is K? You can write Z dash E square upon R. So here we have some particle, let's say Z into E is there, and some particle is coming whose charge is Z dash and it is incoming here. So this is my K. Now, so if we have potential K by R, which kind of orbit is there? Obviously, conic section orbit. We remember
Yes,
this
sir.
thing, है ना? So what is equation of orbit? I can write my equation of orbit is L upon R 1 plus
E
let's
cos
say E
theta.
cos theta. Okay. And what is my eccentricity? This eccentricity, so I am writing eccentricity here with the epsilon, okay? This eccentricity is nothing 1 plus 2E J square by MK square. You can write this thing. Okay. Now this is my eccentricity. Now look at here. Let us assume this is my B, impact parameter B. And particle has mass M and we are sending with some velocity V. Okay. Now what will be my angular momentum of a system? What will be angular momentum of a system?
MVB.
Exactly, because this is perpendicular to each other. So you have angular momentum of a system, MVB. Okay, this is your angular momentum. Now, what is your total energy of a system when you are sending it?
Half
On its
mv
kinetic
square.
energy.
What is this? Only kinetic energy. So that will be half mv square. So this is your total energy of a system, because your force is short ranges, and this is your assumption that at the plus infinity, sorry, at the minus infinity or at the plus infinity, if we are saying this is my reference point, then I can say this is minus infinity, this is my plus infinity. We have this particular total energy is free, this is the energy of free particle, and we have only kinetic energy. So we can put it here, all this value. This value is 1 plus 2 half mv square, and we have j square. So j square is m square v square b square by m, and this is k square. So what is k? Z dash e whole square. कह सकते हैं ना इसे? Yes. So what is my eccentricity? My eccentricity is this particular 2 and 2 will cancel, m and m will cancel. So I can write root under 1 plus m v b upon z dash e square. So this is your e square का whole square. लिख सकते हैं ना? This is my eccentricity. So what I have done, I have written my eccentricity as an impact parameter. Yes. This is my eccentricity. I am writing it with a impact parameter. So sorry, this is half mb square. Okay. And I can write this mb square at my incoming energy. So this is non-value. So this value is non-value. So what is, so my eccentricity I can write in term of energy also, because in the Rutherford scattering it is given in term of energy. So mb square is equal to 2 EB upon z dash e square whole square. Okay. Now this is first part we have done. Now look at here. Look at this particular equation. This equation is very interesting, and I am writing this as epsilon because E is the charge of particle. Now look at what will happen when theta tends to psi. What will happen to R? When theta tends to psi, what will happen to R?
Tends to infinity.
Exactly, R tends to infinity. So this is our condition. And this theta is not this theta. Please, this is my capital theta. Always keep in mind. So theta tends to psi, R tends to infinity. So what will happen? 0 is equal to 1 plus psi cos, so 1 plus epsilon cos psi. And what we have, we can write cos psi as a modulus part, that will be 1 upon epsilon. Mod of cos psi is nothing, but I can write 1 upon epsilon. लिख सकते ना?
Yes, sir.
Okay. Now we have from this geometry, and this geometry will tell you that psi plus theta is equal to pi. And from here, we can write psi is equal to cos pi by 2 minus theta by 2 is nothing but 1 upon epsilon. So from here, we can have relationship. Look at, we have done half of the thing. So we have relationship. And this relationship is basically that will be sine theta by 2 is equal to 1 upon epsilon. So this is what cosec theta by 2 is equal to epsilon. लिख सकते हैं ना everyone?
Yes.
Cosec
Yes,
theta by 2 is nothing but what?
Yes.
Epsilon. And you can also write the value. cosec को cot के टर्म में लिख सकते क्या?
Yes, sir. Yes, sir.
कैसे लिख सकते हो?
Root 1 minus cot square theta by 2.
So cot square theta by 2 minus 1. What will be cot and cot का क्या होता है? Cosec and cot का relationship. So we can write
1 plus cot
just a
square
minute.
theta by
Cosec square theta by 2 is equal to epsilon square. Yes. And we can write it in form of cot square theta by 2. क्या होता है?
Yes,
Cosec
sir.
और cot के बीच में क्या relationship है?
So 1 plus cot square theta equals to cosec square theta.
हाँ, तो what is this? 1 plus cot square theta is cosec square. So cosec square theta is equal to
1 plus cot square.
1 minus na. Just check what is this value. So this is cosec square theta. I just want to write in term of cot square theta. So can I write cot square theta as cot square theta by 2 as 1 minus epsilon square? Just check करो. लिख सकते क्या?
Yes, sir.
How you can write it? What is the relationship between cot and cosec? बताओ.
cosec
One
square
plus
1
plus
plus
Cosec square theta by 2.
is equals to
हाँ, 1
1 plus
cot square theta
cot
by 2.
square theta by 2.
Okay. So cosec square theta by 2 is epsilon square. So cot square theta by 2 is equal to what? कुछ गड़बड़ लिख रहे हो? Just check it.
सर यही है.
Okay, यही है ना? तो फिर यहाँ पर कुछ गड़बड़ हो रहा है. So this value is epsilon square minus 1, I think. है ना? Then this value is there. Now, why we have done this thing? Because I can take a square here and we can take epsilon square minus 1. So epsilon square minus 1 is equal to, we have 2 EB upon Z dash E square whole square. So what we can do? We can easily write cot theta by 2 is equal to 2 EB upon Z dash E square. Now you have done your half of the work. क्या लिखो गया? B is a function of 1 upon 2E Z dash E square cot theta by 2. Cot theta by 2. And yes, this is formula given by your basically Rutherford scattering, the relationship between B and theta. And now you can easily calculate the value of sigma theta. निकल जाएगा sigma theta, sorry, d theta, differential scattering cross section.
Yes, sir.
है ना? So you can get this thing. Just do this exercise with yourself. है ना? It will. You have to just go and differentiate this thing, and finally you will get this particular thing. So I am just giving you the final answer. So B is this one. So d theta is given by B upon sine theta dB upon d theta in the mod part. So you can get d theta, differential scattering cross section is very famous one. And this is 1 upon 4 Z bar E square by 2E whole square. And this will be cosec to the power 4 theta by 2. So this is your main thing. You can easily calculate. Just do it as your homework. So now you can see how you can use all the concept of your central force problem to calculate the system, isn't it?
Yes, sir.
है ना? Suppose everything is, and E is your total energy. This is nothing but your kinetic energy. So tomorrow we will try to do some more problem in the classical scattering, and then we will try to go for mainly quantum mechanical scattering, which is more and more mathematical in nature. But yes, the thing is exactly same. The basic concept is exactly same. What are the basic concept? Angular momentum of a system is conserved. Incoming particle is free particle. Outgoing particle at very far away is also free particle. But incoming particle is something like a plane wave. And what should be the outgoing particle?
Plane wave at large distance.
Outgoing particle will be plane wave at the large distance. Incoming particle is plane wave. What about outgoing particle? यहाँ पर outgoing particle plane नजर आ रहा है? एक ही डायरेक्शन में जा रहा है क्या?
No, sir.
No. So किस सिमेट्री में जा रहा है? Spherical wave. Spherical wave. So that is also free spherical wave at the very large distance. And we will just try to see how this differential scattering cross section is calculated into quantum mechanics. ठीक है? So आज के लिए इतना ही रहने देता हूँ. बाकी चीज को कल हम लोग ट्राई करेंगे करने की. हाँ बताइए.
सर ये जो डी थीटा का एक्सप्रेशन हमने निकाला है बी अपॉन साइन थीटा डीबी बाई डी थीटा, ये सिर्फ और सिर्फ स्फेरिकल पोटेंशियल्स के लिए वैलिड है ना? हम उसी में यूज कर सकते हैं. या हाई
किसके लिए?
पोटेंशियल के लिए?
ये नहीं, ये तो आप हर एक के लिए यूज कर सकते हो, ठीक है, बट थिंग इज दैट कि आप अगर स्फेरिकल पोटेंशियल नहीं होगा तो बी और थीटा के बीच में रिलेशनशिप कैसे निकालो?
यस सर।
दिस इज, इसमें तो हमने कहीं ये एजम्पशन थोड़ी लिया है कि कंजर्वेशन ऑफ एनर्जी है या नहीं है, या फिर कंजर्वेशन ऑफ एंगुलर मोमेंटम का यूज किया है, ये थोड़ी किया है। हमने क्या किया है, हमने तो
Yes, sir.
जस्ट 2 पाई बी डी बी आई नंबर इज इक्वल टू डी थीटा डी ओमेगा इंटू आई, यही किया है ना?
Yes.
So this is for the every type of potential, but thing is that ये फॉर्मूला तो तुम लिख लोगे, बट एक्चुअल चैलेंज इज दैट हाउ यू विल राइट बी एज अ फंक्शन ऑफ थीटा ना?
Yes, sir.
Now this is not a challenge, the challenge is this particular thing, how you will write b as a function of theta. अब जैसे कि लास्ट प्रॉब्लम को ही देखो जिसमें हमने रदरफोर्ड स्कैटरिंग किया था, we have taken this fact in account that my angular momentum is conserved, then only we can use this thing, isn't it?
Yes, sir.
तभी तो आपने b की वैल्यू क्या लिखी, j की वैल्यू आपने लिखा ना mvb, why? Because your angular momentum is conserved, और ये पूरी जगह पर सेम एंगुलर मोमेंटम रहेगा।
Yes, sir.
Okay, so due to mathematical compulsion it is very difficult to write b as a function of theta if you are not a symmetrical system, a spherically symmetric system, ठीक है?
Yes, sir.
Okay, so I will just give you one picture जो मैं ठीक से बना नहीं पा रहा हूं, so I will just give you that figure, तो आप उससे आप देख करके समझ लेना क्या एक्चुअली हो रहा है। ओके, व्हाट इज डी थीटा
sir.
एक्चुअली, है ना, उसके बारे में आप देख लेना। ठीक है, तो आज के लिए इतना ही रहने देते हैं, कल हम लोग इसके आगे कम करेंगे। ठीक है,
जी सर,
Thank you, sir.
थैंक यू।
थैंक यू सर।